Okay, so today we're going to do Lab 6, magnetic fields in a solenoid, but before we talk about solenoids, I want to review a little bit about what we've been doing so far, which has mostly been electric fields, right? And we started off with charge. How does charge relate to electric fields? Anybody? If you have two charges, right, there's an interaction between these two charges. And so there's a force, right? So we talked about Coulomb force, which looked like this, right? And then from there we talked about electric fields. How are electric fields related to forces? Force is perpendicular to the field. Not quite what I'm looking for. So if I have a force law, right? Does that look familiar? It's good we're reviewing this, right? And so that makes the electric field for a point charge K Q2 over R squared in the R hat direction. So this would be like Q1. So this was an interaction. It had two charges, and there's a force between them. Whereas this is just for one charge, and the electric field exists everywhere in space. And so if I drew a picture here of maybe like a proton, there would be an electric field coming out of the proton, and it exists everywhere. And what does that tell us? It tells us if we put a charge, another charge, Q here, well, we take this electric field, multiply it by that charge, and we'll get the force on that charge, which is good old Coulomb's law. So this and this are almost, to me, the same thing, except one is an interaction, one is a field. Any questions so far? All right, and you can also do this with potential energy and electric potential. So these guys were vectors. And vectors are useful in physics, but most of the time we don't like to play with vectors because, what reason? We have to worry about two things, right? Magnitude and direction. So if we can work with something that's not a vector, we're a little bit happier because we're just working with a magnitude. And so you can work with the voltage, which is similar to the electric field, except it's not a vector, and it only has this 1 over r instead of 1 over r squared. And this guy is K Q1, Q2 over r. So this is an interaction, because there's two things, two charges. All right, what's the connection between the potential energy and the potential? It's the same kind of relationship. Yeah? U is equal to Q times V. All right, and these are connected. F is equal to the minus the gradient of U, and E is equal to minus the gradient of V. All right. So they're all connected. That's electric fields. What did we talk about after electric fields? We talked about magnetic fields, right? So magnetic fields had a different force law. What was the force law for magnetic fields? Did it have a Q in it? Yeah, it did. And also had, obviously, the B field in there, right? But it had this extra V. What is V? Is it the voltage? No. It's the velocity of the charge. Okay, so what happens if a charge sits and doesn't move in a B field? There's no force, but that charge in electric field has a force. So they're similar, but this one is a little more complicated. You have to worry about the velocity. Any questions on this? All right. Yeah. What's that?
Is there still a distance on that force point?
What are you looking at?
The one you're pointing at.
Okay, is there distance in here? So this is the force.
Yeah.
This is the charge. This is the velocity, meters per second. And this is the B field. This is the cross product. So it's a form of multiplication, and it's defined, if I have room somewhere, A vector cross B vector is equal to A B sine theta. So physicists get lazy. So we don't like to say in the radial direction, so we invented this symbol. So we don't have to write that every time in the radial direction. And we get lazy with signs too. So when we get tired of writing sine, we just write x between them. That's called the cross product. And so my joke is, if you stare really hard at this x, can you see the sine theta? It's in the x, okay? Any other questions? That's a good question. All right, so then we talked about magnetic fields in a wire. So if you have, oh, by the way, what creates a magnetic field? Currents, right? Whereas with electric fields, it was charges. This charge creates this electric field. And so whenever you have a current, you create a magnetic field. And the way you find the magnetic field is you put your thumb in the direction of the current, and whatever way your fingers want to naturally go, always using our right hand, is the direction of the B field. In this case, it's around the wire, kind of coming out of the board at the top, going into the board at the bottom. And then we can derive from Ampere's law that the magnetic field is equal to mu naught times I over 2 pi rho, where rho is the distance from the wire. So this is a review, which makes sense that it's proportional to I because the current creates the magnetic field. So if you have more current, you have more I. This also decreases with distance. So here I wrote Ampere's law in its full differential form. Closed loop integral of B dot dA is equal to mu naught times the charge enclosed. If you don't like calculus, that basically is just saying B times the length, L, is equal to mu naught times the charge enclosed. So what is this L is probably what you're asking. And so what we do is we draw that Amperian loop. It's kind of an imaginary loop around the wire. And we pick it in such a way that it's always kind of with the B field. That kind of takes care of this dot product here. This dot product always goes to 1. The dot product is a cosine if you stare at it hard enough. And that gets us to here. And then all we have to ask ourselves is, what is L? L is this length of this imaginary Amperian loop. What is the length of a loop? Circumference, right? It's 2 pi, the distance rho I'm using. And so you just divide by that and you get B. So this law comes from Ampere's law.
What is the symbol that you're dotting the B with in the first equation?
This thing? It's a dot. This one?
No, it looks like maybe an M or something.
This one?
No, on the left. Right.
This is dl. So for those who know a little bit of calculus, this is a differential length. It ends up just being L. So, good questions. All right, let's do a solenoid now. So this kind of ends the review, just kind of getting us up to solenoids. And a solenoid is just a wire that's been looped around many, many times. And so if we wanted to find out the B field from a solenoid, we can do the same thing we did for the wire, which was the right-hand rule. And so if I put my thumb in the direction of the current, which way is the B field? It's around the wire still, something like this. And then I'm going to get over to here, and I'm going to do that, and I'm going to notice that inside, so my loop's going like this. Inside, there's a B field that points up. And if as I go around the loop, you see this? It's always pointing up on the inside. And so what you're going to get is a strong B field inside the solenoid. You see it? Now, why is that better than from the wire? So we did last week, we did the wire, we measured the B field. What did we notice about B fields from wires when we tried to measure them? How many Teslas do we get? Like 0.00 millitesla, like very, very weak. These guys end up being pretty strong. So by looping the wire, you're sort of each loop gives you more B field. So the more loops you add, the stronger the B field. The other nice thing about this is the B fields are basically uniform inside this. What does uniform mean? They don't depend on space. They're not a function of how far you are away. So whether I'm measuring it right here, or right here, I'm going to get roughly the same B field. It doesn't vary throughout the solenoid. Now, if this was an infinite solenoid, these guys would go off to infinity, right? And you'd have no B field on the outside. But in real case, you're always going to have a finite length. And so these guys are going to loop back around. And do that dipole thing, just like a magnet, right? The B field will be very strong on the inside. Out here, it'll be almost zero, very small like the wire, 0.00 millitesla. And so we approximate it as being basically zero outside. All right, and you'll do this today, and you'll see it. All right, so the B field from the solenoid, if we write it down in a formula, it's always proportional to this constant, this mu naught, which is the permeability of free space. All these magnetic things always have that guy, that constant. Times n. N is the number of turns per unit length, little n. So I put big N as the number of turns. L is the length. That's your length. Number of turns, 1, 2, 3, 4, 5, 6, 7, 8. So this picture has big N equals 8. And if it was 1 meter, it would be 8 turns per meter. And then, of course, there's an I there. Why is there an I there? Because the current creates a B field. And then I added a little Z hat, which gives us the direction, since magnetic fields have direction. So there's your Z. Any questions on this? All right, one other thing I want to mention is that solenoids are also called inductors sometimes. So whenever you put them in a circuit, they're usually called an inductor. Yeah, an inductor. And we'll talk more about inductors next week, so I don't want to get into it in too detail. I just want you to be aware of that. And then if we were to graph the B field versus current, what will we see? A linear relationship. As you double the current, you double the B field, because currents create B fields. And if you did B field versus the number of turns per unit length, if we increase the number of turns per unit length, we also increase the B field, so you'll see a linear relationship. Are there any questions? Yeah.
In our lecture, the professor said that the inductors, she rarely sees them used. Is that your experience too?
Well, we'll use them next week, so we will use them.
I mean, I guess in real life.
Oh, in real life. Well, I mean, it depends on what you do for a living, right? I mean, if you're going to go on to do a lot of circuit stuff, then yeah, there are definitely parts of circuits that use inductors. I mean, do physicists use inductors a lot? I mean, I personally don't in my daily work. So I think it all depends on what area you're pursuing. So maybe she doesn't, but I think maybe what she's trying to tell you is that inductors aren't going to be heavily tested on, maybe. I think that's probably more what she's getting at. Any other questions? All right, so our inductor is going to be a slinky, which is kind of fun. I like slinkies. They're fun to play with. And they work great because they're made out of aluminum, which is a conductor, and they're nice and big so we can fit our B field sensors inside. So this is sort of a setup Now you're going to need something to hold it open. You can have a weight here. Some people like to use a meter stick. Some people prefer to use just tape it to the thing. Whatever works for you, I'm okay with as long as it works, right? And what are we going to do? We're going to measure the B field in it, and then we're going to turn up the amps, right? Turn up the current, and we're going to see this relationship. Then what are we going to do? We're going to change the length, which is another way of saying we're changing the number of turns per unit length. The number of turns is fixed. It's something like 86 or something. You actually have to count them. And I recommend starting out longer and going shorter versus shorter than longer. It seems to work out a little bit better. But again, that's up to you. So you'll stretch it out to maybe twice this length, and then you'll move it in and get 5 or 6 data points. Does that sound pretty straightforward? All right, you guys can get started then.